Okay, Dan, the floor is yours. Take it away.
Okay, thank you, Arthur. Really happy that you invited me here so I can
The pleasure is ours.
hang out in Warsaw for a while. It's really amazing. So guess I should have put this up. What was my title? It was
Directed graphs, variations on graphs, and their algebras.
so you'll have to bear with me as I learn how to write again. So because you can listen to me 3 times this week if you want, though maybe some of you won't have a choice. I thought I would try to give a very rough outline of the 3 main parts of the talks. So the first is, and I actually wrote it out. Yeah, so let's say directed graphs. But today, directed graph, first generalization, as far as I can tell. And it's a kind of a historical picture. But I hope I can present this in a way that isn't the usual way. So maybe there'll be something slightly different. See, my main point is to see where the ideas from the directed graphs have been generalized. And so for the next part, I want to go toward the larger generalization. And here I'm going to abbreviate. These are I call them LCSC. And this stands for left cancellative small category. But we'll get to that and I'll talk about this and explain why the left is important. A lot of people are working on the similar ideas over a long period of time. And there are various ways of going about taking this more general kind of object and doing something with it. So my point of view, or what I found most convenient, is to use groupoids to pass between these sort of basic data and then C-star algebras. So I'll say something about that. So again, of course, I won't give a course on groupoids in a couple hours. And then, of course, the C-star algebras. Yeah, so hopefully with a bit more detail. And then the third part, I wanted to tell you about recent work that illustrates this. So there's an element of generalize for the sake of generalizing. And I was very pleased that finally one of my graduate students found beautiful examples that show up in this context that are something that really feels new. So I want to tell you something about that. And I think there's some really interesting things outside of just the C-star algebra. So some examples. And these are related to continued fraction expansion. Okay, so my first attempt to be clever. Okay, so I am writing too small and too close together. Of course, continued fractions have shown up in operator algebras already, but this is somehow slightly different appearance. So that's sort of basically where I'll be going. Okay, so what I want to begin with, I think everyone does this. It's my particular origin myth for a graph algebra. So, I didn't make up this myth. I took it from Kunz's. So, it starts with Dixmier. This was in a 1964 paper. So he has this theorem. It says that there exists simple separable infinite C-star algebra. It's sort of funny for us now, but at the time, what did we know? We had the Topological algebra, which is
Not simple.
separable and infinite, but not simple. And the Kalkin algebra, which is simple and infinite, but not separable. So this was actually an important theorem. Let's see what we had. And so his proof was, very simple. And Kunz presented it in his paper too.
We also need unital, right?
Sorry?
We also need unital, right? The C-star algebra of the compact operators is.
That's not infinite. The compact operators. So I guess infinite for a non-unital C-star algebra would mean that the unitization has a non-unitary isometry. Is that the usual notion?
I'm not sure now.
I think, yeah. So, but no.
Infinite does not mean that the dimension is.
Sorry,
Yeah, that's a
good point.
doesn't mean infinite, yes.
Okay.
Yes, infinite means the C-star algebra A contains non-unitary isometry.
Oh, I see.
Like the Texas algebra.
So that's the key thing. So there's unilateral shift was the first example, it's the most important, famous example of an isometry that's not unitary, right? Because the pigeonhole principle fails in infinite sets. Right?
And so, naive question. What if I take the operator of bounded algebra of bounded operators on the Hilbert space? Which adjectives will not fall?
Because the compact,
Not separable.
actually, it has only one ideal, the compact operator.
But it has an idea.
It's also not separable.
It's also.
No, but the bounded operators, if you divide by the ideal of compact operator, that's where you get this Kalkin algebra.
So, what is the ideal? The compact operator.
Compact operators.
I learned what are compact operators 20 years ago.
So if you look at the finite rank operators.
And I was.
Not very fast.
Sounds like Philadelphia.
No.
Yeah, so think about all the finite rank operators.
Finite ring, finite.
Right.
Finite ring. Okay. Oh, yeah, I see.
Right, so that's actually an ideal.
Oh, I
So
see.
it's not closed.
Okay,
If you close it up, you get the compact operator.
okay, I see. Okay.
That's the simplest description. That is good for Hilbert space. It's not good for Banach spaces in general. But, that's a good way to go at it.
So take all finite size matrices and non-complete.
Yeah, but of course, they don't have to be relative to the same order basis. It's all finite rank. But let's see. So that's the unique ideal, closed ideal in B of H, and this is the quotient, which is then simple.
Okay.
And Kalkin is the first person who studied it.
And by the way, if I might just throw in, this is a very important algebra because this is where you look at indices of Fredholm operators. So in the index theory, like Atiyah Singer and so on. And you talk about Fredholm operators, which are invertible modular compact. So they're invertible.
I don't mean the image here is an invertible. Yeah.
Yes, that's why it's important.
So the index now classifies the connecting components of the invertibles.
Okay.
Right, so let's see how Dijkstra proved this. I could probably squeeze it in here, but I can always move it over. Let's see, so we choose,
Well, you have countably many.
right? No, they're only finitely many.
Yeah.
Under the universe.
Probably finitely, yes.
So choose isometries. In the bounded operators on some Hilbert space. So two of them, S1 and S2. So that the range of S2 is the orthogonal complement of the range of S1. Right, so on an infinite dimensional Hilbert space, of course, you could do this. And then of course, the ranges we can think of as correspond to initial and final projections. So we got this famous identity S1 star, S1, whoops, S1 star. So
Eraser.
I'm going to try.
Oh, yes. You could do it in real life. Undo, you do something on undo. Because you're speeding tickets. No, undo. Go slower.
Okay, so I'm going to erase. It's just too stupid. So I'm just going to call this identity star. These are just the projections onto the ranges of the two isometries. So now Dijkstra says, so let's let A be the C star algebra generated by these two operators inside B of H. And right, so if that were simple, that would be his example, but we don't know if it's simple, but because it's a unital C star algebra, it will contain at least one maximal ideal. And so we can choose a maximal ideal. And that's since A contains an identity. And then this equation star holds in the quotient. Oh, of course, you have to replace S1 and S2 by their images, S1 plus I, S2 plus I in the quotient, but the same ideal holds, same equation holds, and also so as well as the fact that there are isometries, SI. After this, still doing it. I'm thinking so hard about writing slowly, which I'm not doing, that I can't think about what I'm writing.
Just, is it possible that the pen has a maybe like a button there to change those margins? No.
Yeah, maybe I can make a thinner line, but then it would be harder to read. Maybe. Okay, so we still have isometries. They're non-unitary because this holds. And now it's simple because we divide it by a maximal ideal. So A mod I is the example.
I don't understand why this two-term equation became one-term equation.
Sorry?
Because
No, so star is still this two-term equation.
Oh, I see.
This equation I didn't write before. This is the usual way of saying that S sub I is an isometry.
Yes.
Because this says that, my finger is just as sensitive as this.
And
So what is S zero? I didn't.
It's not zero, it's I.
But the first one, oh, I see.
it's badly written.
Oh, I see.
If I can do it. So and this just means SI is an isometry.
And may I ask how the maximality of I implies that?
No. The fact is that maximality of I implies that this is simple. I did not write that either. Okay, so yeah, thank you for keeping me on track.
But okay, so this I
So it's simple. Because I is maximum. So that's the point of the maximality, is to get simplicity.
so then to paraphrase my question, so why simplicity implies SI being I?
It doesn't.
It doesn't. So the three properties is simplicity, infiniteness, and separable.
So separable comes because there are only two generators, right? Simplicity is by the maximality, and infiniteness is because being in isometry and having this relation persists even after dividing by the ideal.
Sure, but I'm not sure why it's an isometric, basically.
Okay, so this equation, let's see, so if you look at,
The class of the unit in
yeah, so let's say this equation X star X. Sorry, I might get better as we, move,
Oh, yeah, definitely.
but it'll take a while.
Because I'm outside of this area, so perhaps silly questions.
No, but this is good, Alan.
So what does this mean? X star X equals 1. So we look at, say, the norm of X applied to a vector squared. So the usual way is to rewrite it with the inner product. And now the adjoint lets us pop this over to the X star X. So maybe this isn't answering your question. So X star X being 1 means that it's just the square of the norm of C. So this equation tells us that X preserves length.
Sure. No, so, but my question, I guess, then is why S star S is 1?
Oh, so,
This is useful too.
right, so I chose isometries.
Oh, you did. Okay, I see. Oh,
So it's hidden here in this question. Yeah, I'm sorry, I didn't understand the. But probably I should have introduced this identity when I talked about it to make it clear that that's what I was connecting.
That's true by assumption.
Well, that's never a good answer. But yes, but you're right, it was hidden in the assumption. Okay, so that was Dix-May's result, and now. Uh-oh, my symbol's not there.
You know, just,
Was this just a plus?
Yeah. Yeah.
Oh, now I have.
yeah, number two.
Okay, so now in Kuntz. And this was in 1977. It says that A is already simple.
13 years after.
Yeah,
So it wasn't that simple.
no. So I wrote the proof of Dix-May's result. Well, I think that was his paper had more than that, but I won't write out for you the proof of Kuntz. Though if you've been in Piotr's class for the last couple of years, I'm sure you've seen the proof more than once. But I want to explain why it's true. Okay, so let's, instead of writing the proof, I'll just say why. And the answer is S1 and S2 generate a copy. Well, I shouldn't say copy. Can you, no one could read this. But can,
Generate.
if I just say it, generate, that's okay. Generate, F2 plus. So this is the free monoid on two generators. So let me show you a picture of this. I think that's
This is sort of the ping pong lemma, it seems like.
ping pong lemma.
Yeah.
I don't know this number. Maybe I'll show you a proof of the ping pong lemma.
You take a word and you follow the word letter by letter, it will map half of the Hilbert spaces to the other half on the orthogonal pattern and back and
Yes, yes. But I want to draw a picture that will make the next step clear as well. Yeah, but this is such a fundamental example.
for sure.
There's everywhere. Okay, so I'm going to draw it this way. I'm going to start with the Penn decided for me where it was going to start. It was the Hilbert space. And now we have these two subspaces, the ranges of our two isometries. So let's put the first one here. And the second one here. So these are really sitting inside. It should be. Any competent person would make this pretty diagram. Okay, so now we know that, for example, S1 pushes the entire Hilbert space here. So it pushes this whole picture here. So inside of S1H, we have, say, S1 of S1H, so S1 squared H, and S1 of S2H, so S1, S2H. Those sit inside these. And likewise, S2 pushes it all up here. So we have S2 of S1H. Sorry. And S2 of S2H, so S2 squared H. And we can keep doing this, right? So of course you could I'm not going to draw all the things. We have things going into all of these places. We can move to the right or up from each of our things, and we keep doing this. Right? Now I think it's actually elementary to convince yourself that from this picture, we have a proof that we actually have the free monoid on two generators.
Yeah.
It's a binary.
Yes.
Now out here, well, of course, what we have is the binary rooted tree. Right? Rooted at this first place. So we have the boundary of all infinite paths. Let's see, my writing down. I'll just call this X. Is what we call the boundary. Let me remind myself where the story is going. Okay, so what do we think of as X is all infinite words in S1 and S2. So that's by infinite paths, that's a Cantor set. Maybe I don't have to. So now we have tau 1 and tau 2 are my names for the partial homeomorphisms we get from these two generators. Right, so say tau sub I. You'd think I would switch to a different letter since I is so difficult, but I can't. Okay, so tau sub I of say S J1 S. K2. It's just SI and S. So just basically just this shifting to the right. As for I equals more than 2. So we think of together, we have this compact Hausdorff space X. We have these two partial homeomorphisms. So sometimes we refer to this as a partial dynamical system. And I'm studiously avoiding defining these kinds of things. But they are well studied and precisely defined.
And why is it called partial homeomorphism?
Because these are not homeomorphisms of X. So for example, tau sub I, its domain is all of X,
Yes,
but its range is only half of X.
okay, okay, yes. Of
I'm going
course.
to try
Yes,
rubbing out my finger.
yes.
That is easier. So there is a kind of cross-product construction. So cross-product construction is what we do in C-star algebras when we have a group acting on a space or on another C-star algebra. And that's classical, whereas partial dynamics is maybe not completely classical yet. But it takes less and less time to become classical these days.
And when you say partial homomorphism, do you mean homomorphism onto its image?
I mean a homeomorphism between two open subsets of the space.
But wouldn't it be just simply homomorphism onto its image?
Yes, but it's important that the image be an open subset.
And we keep with X, we keep X with the product topology.
Yes, yes. It's the usual way. It's a Cantor set.
Yeah, exactly. That's what Cantor said.
So I'll just say usual Cantor set
About
of all. Oops. There's a. Okay, so we might denote this cross product C of X semi-direct product. Really, it's this monoid, the three monoid on two generators. So of course, this is isomorphic to Kuntz's algebra O2. This is where this example came from. Now, but in this context of partial homeomorphisms of a space, it's important that properties of the dynamics imply some properties of the C-star algebra. Can't leave that C alone. All right, this is our C-star algebra. In fact, it's of course instance of two. So, for example, a minimal action, that means that orbits are dense. Well, so if you start taking a typical point like this one, defined by the sequence J1, J2, J3, and you push it with various ones of this tau1, tau2, you're basically building a sequence that has an arbitrary initial segment and then whatever you started with. And it's clear that can be pushed into any basic open set. So every orbit is dense. So that's the methodology. We also have something called topologically free. And that means that the aperiodic points are dense. So of course, a point is periodic if eventually the sequence of symbols repeats a fixed pattern over and over. And so an aperiodic point is one that is not like that. And it's clear there are only countably many periodic points. So the complement of those will be a dense. So that's this topological business. And the third important property is amenability. But I'm not going to say anything about that. That's just more complicated, and maybe in the more general setting later in the week, I could say something, but even then I'm sort of doubting all that time. But the point is that these three together, these imply simplicity.
And so what is topologically free?
So it says, so in this setting, we can describe it as the aperiodic points are dense. Now, another way of saying aperiodic is the isotropy of the action at such a point is trivial. So isotropy means which elements of the monoid leave a point fixed, is the isotropy at a point. So an aperiodic point is one at which no non-trivial element of the monoid fixes that point. So the proper definition of topologically free is that the points with trivial isotropy are dense.
I know you didn't define its amenability, but does it imply that this cross product is nuclear?
That's amenability.
That's the definition.
No, it implies that.
Right?
Yeah.
That implies the amenability or the amenability.
Amenability implies that the cross product.
That's okay. It's just so it's stronger than nuclear.
It's possible that they are equivalent in this context. I'm not sure. So Claire and Thurman de la Roche has done a huge amount of work on this question. And I believe she's answered it in this context, but I'm not absolutely sure. I get confused with subtle details, but in this case, certainly the amenability implies nuclearity of the cross product. More importantly, for our example, it implies that the full and reduced cross product constructions give the same result.
Yes.
Which is the main obstacle to simplicity that the amenability addresses. So this is maybe an outline of how to prove Clinton's theorem in a way that generalizes far beyond the cases we're talking about. Okay. Now,
sorry, can you tell me one more time why the orbit is dense?
yeah, so let me write it.
So we should you can that every open set in product topology intersects the orbit, right?
So let's take a typical basic open set, which we might call
Should be a long something like you can put your letters in front of arbitrary words to get arbitrary initial segment, for instance.
let's say Z of I1. I'm just going to revert to the indices instead of writing the
Of course.
operators.
Yes.
So as a typical thing. And let's take a point. This is so hard to write. J0, J1, J2. Okay. And now let's look at tau I1, tau I2. Oh, so an open set, of course, only has finitely many ordinates, right? Up to IN. So up to tau IN. And apply it to the point J0, J1, J.
So you mean that that's the beginning of your sequence, right? When you write Z and then
This is opens, yeah, this is
take the set with all such beginnings.
all such beginnings. And then something else.
Yes, exactly. Anything else. Mhm.
We take any point whatsoever and push it with this combination of our generators of the action, and we get exactly that thing. But I1, I2, IN, J0, J1, and so on, which belongs to so any point.
Oh, yes, of course, yes.
The open set.
My stumbling block was that I picked up a fixed I, whereas I can change.
Yes.
Of course, because an orbit that again, thank you so much. I'm sorry.
And somehow this is.
Yeah, it's clear.
Same with the density of the aperiodic points.
Yeah, the same, yeah, but you know, again, this is my mental picture for every situation like this, right? Okay, so I want to mention now what I think is the key idea behind Kuntz's theorem. So I'll just express it this way. So from this pair of operators, S1, S2, satisfying the identities that Kuntz gave, with some work, we build in general locally compact Hausdorff. Okay. That's remarkable, I think, right? So the S1 and S2, what do we know? We know that S1 star S1 equals 1. Isometry, same for S2. S1, S1 star plus S2, S2 star equals 1. That's Kuntz's identity or Fitzmaye's identity. That's very elementary combinatorial data. And from that, we build something, place to do analysis. Compact Hausdorff space. Now, in general, when you're given these generators and relations, that's the first job, is building something more interesting out of it so you can start doing analysis. And it's tricky, right? So if you look at Kuntz's paper, it's just brilliant how he extracts from this so much more and then proves his theorems. But I think it's also good to have a recipe for finding that stuff instead of having to be brilliant each time you come up against it. And that's my basic motivation in studying all this stuff, is how to survive without being brilliant. Okay, and of course it also gives in general partially defined dynamics. And then there are standard procedures for building from this kind of ingredient, C-star algebra and properties. So it gives us a systematic way of starting with something like what Kuntz started with and building a C-star algebra and learning something about it.
This is maybe a silly question, but there is a comma after locally, comma, compact. Is there a reason for that? Or
Yes, so of course, in this example, we get a compact Hausdorff space, but as we'll see in a little bit more generally, we'll sometimes get only a locally compact Hausdorff space. It did, well, you'll see. I mean, it's not obvious here, but it'll come up in And it's not a very deep reason. So it's not a big deal. Okay, so. Okay. So the sort of historical ideas I'm trying to go about are treat sort of two kinds of generalizations. So here's the first one. And it really is, you might say, how can one not notice the Bernoulli shifts in Kuntz's original paper? And so, of course, I'm sure Kuntz did, and he teamed up with Krieger, who was a dynamic person. And so they treated subshifts of finite type. Let's see, so Kuntz and Krieger. The paper appeared in 1980. So SFT shift to finite type, and really subshift to finite type. So what did they do? So we let A be an n by n matrix with entries from 0 and 1. So that's how you define a shift. So especially in this first work, they assume that A is irreducible. So that means that say for all I I and j from 1 to n, let me not write that. There exists k such that the k power of a ij entry. Yeah, so I'm still not learning. So really it's saying that given any ordered pair of indices, there's a directed path. Oh, I haven't talked about that here. Some power of the matrix is non-zero within it. This is the standard definition of irreducible for a zero matrix. Okay, and then let's see, so we let X be the n-fold Cantor set. And we let X sub A be little x in big X, such that, right, so now this is a sequence from the numbers 1 up to n, the indices 1 up to n. So we want A, so maybe it's convenient to continue with parentheses that X, I, comma, X, I plus 1. So it's those sequences, but the successive entries in the sequence define an entry in A that's equal to what? So A is telling you what are the allowable sequences in the set. So you might say that irreducibility means that given you can always find a sequence that's allowable that goes from I to J. Any ordered pair items. So that's a compact subset. So X sub A is closed subset. And it's invariant. Under these shift maps, L1, Ln. So we get a new partial dynamical system, and we'd like to look at its cross product. So we want
So wait, so this XA is always well defined for any matrix A. But if A is irreducible, it has some extra properties.
yeah, well, so for an arbitrary A, there are some problems.
Like it can be the empty set.
Yeah, or you know, things can sort of, there may not be any, yeah, for example, or you might just be missing something that might be there. So this is it, and it gives a bit more than that as well. So it's just a convenient assumption that they made for the first go at doing this stuff. Now, it's actually easier, I think, to study this stuff in terms of a directed graph instead of a zero matrix. And this is most of the work that's generalized these constructions has been in the context of directed graph. So there's some notable exceptions of looking at matrix picture. So let's see where we get a directed graph out of this. So let's.
It's compact household because this X is still like a counter set. So it's compact. The close of the compact household is compact household. So you can take it. Okay.
And the assumption of irreducibility will mean that it's really is a Cantor set. There are no isolations. Okay, so let's rephrase as a directed graph.
Just out of curiosity, are there some examples of irreducible such matrix that is not, let's say, block upper triangular or blockwise lower triangular?
Oh, sure. So the matrix of all ones that gives you all of X back. That's certainly irreducible.
I mean, not irreducible, but
Not irreducible.
but it cannot be written as blockwise upper triangular matrices or blockwise lower triangular matrix because these.
I mean, like sort of on the diagonal.
Yeah,
Um,
that's the obvious way of making it not irreducible, but I'm not sure it's other ways of.
I guess you might have, no, I don't, I think the answer to your question is that they all can be put in that form for an appropriate implementation of the indices.
Okay.
So I'm not absolutely sure.
Okay. Okay.
So now a directed graph is given by some information, right? A set of vertices, a set of directed edges. And well, the direction comes from two maps that tell you where the edge begins and where it ends. So let me tell you what those are. So we let E0, the vertices, just be our numbers from 1 up to n. We let the edges E1, these are the set of all ordered pairs of indices such that they're allowable. So A of ij. Whoa. I'm trying to think this, like having a pen that leaks ink. And then I have to tell you what's the beginning and end of an edge. So the source of the edge I, J, could be J, and the range of I, J, could be I. And I should say this is what I refer to as the Australian convention. So I will acknowledge but not apologize for using this convention instead of the other convention that many people use when dealing with graph objects.
So what is the graph of the Teplitz algebra in your convention?
Oh, okay, so that would be
Okay.
that's the opposite. The Worcester is in the opposite. And the reason for this is because when we generalize this outside of the realm of graph algebras, this actually makes more sense in a certain way. But again, it's a convention. You can always choose whichever way you want, and it really doesn't matter, except that your head will just go between. So the idea is that we think of IJ, our edge. We thought it was a morphism. From the object J to the object I. What else did I want to say about that? Right, let's move on. So
Basically, will allow loops, but not multiple edges.
not yet, not yet. I'm just reinterpreting the Kunz-Krieger situation. We'll come to the rest in a moment. This is part of my historical tour.
And by the name of Kunz, you wrote some abbreviation like ST something.
Oh, SFT. It's called shift of finite type.
Oh, okay.
But I think it used to be called subshift of finite type. But and I'm not a dynamical person, so I don't really know how to language it. It's a subshift of the Bernoulli shift. The finite type is this matrix, a finite matrix that tells you what are the allowable. Okay, so now we a very important extra bit of structure is the set E star, which is all finite directed paths. Right, so now we know how to concatenate two paths as long as the source and range map up appropriately, so one really does. So we think of concatenation. Of paths. That's really composition of morphisms. And then we let E infinity be the infinite directed paths.
But only in one direction or both?
No, just the one direction. Just the way we've been drawing them, right? You know, I0, I1, I2.
But it can also go backward.
Of course, but I'm doing what we were already doing, not something new. And that, of course, is exactly our space XA in this example. Okay. Yeah, so I guess I'm rewriting so for an ordered pair of indices, which we think of as an edge of our graph, we have the partial homeomorphism tau sub ij.
We'll be gluing the beginning.
I'm trying to get back to where I was.
Okay.
So it takes all infinite paths that begin with J and sends them into the set of all infinite paths that begin with I by taking j, say x to ij x, where x is an arbitrary infinite path. Okay, so now what do we have? We have the set of identity functions on the sets. Sorry, I'm trying to write this carefully and the board is fighting me. So the set of all identity maps on these sets I infinity they're pairwise, well, let's see. Let me write it separately.
So for the infinite paths, we have a well-defined target, but not source.
Well-defined range.
Means
They have no source.
Okay.
They have no source. Well-defined.
yeah.
So amongst these, we know that, say, identity, these are actually, of course, identities are idempotent. And if we compose two different ones, that's empty if I is not equal to j. And we have the tau. These are partial homeomorphisms. And then we have these three relations. First of all, no, two relations. So tau ij this is so hard. I don't know why I had all this trouble. When this gets close, it starts writing.
But so yes,
The way to decrease the sensitivity.
I have no idea.
Okay, I'm going to try again at the beginning.
I think bigger is easier. You see,
Here's a little bit easier. So if we compose tau ij inverse with tau ij, get the identity on j e infinity. With the identity on I e infinity, that's equal to the union 1 to n of the tau j composed with tau I j. So hopefully this looks familiar if you've seen it. These are the relations that Kuntz and Krieger gave for their example. This just says that the set of all infinite sequences beginning with I is the union over all possible j of the sequences that begin with ij. Right? Just you decompose it according to the sequence.
so what is this index under the sum?
You're right, that's j.
Okay,
So now I can write the Kuntz-Krieger theorem.
yeah, exactly halfway through, by the way.
Okay, yes, well, luckily can cover less material over 3 days and continue next time. With variation, with some adjustment. Yeah. So H should be our Hilbert space, infinite dimensional. And
Unseparable.
doesn't have to be separate.
What I would say. It's like the Kunz example.
And we write it as direct sum of infinite dimensional subspaces. And let's see. We choose partial isometries. No, exactly what I don't want to do. So I'm maybe not quite stating it exactly as Kunz and Krieger did. I'm going to index my partial isometry. No, in fact, I looked at their paper. This is exactly what they do. So the partial isometries are indexed by edges in this graph. And they should mimic these relations. Such that so S I J star S I J equals the projection onto HI and the sum J equals 1 to N of S I J S I J star is projection on the HI. So that's just modeling these relations from the dynamical system with operating on space. So then the C-star algebra generated by this set of SIJs is simple. It's independent of how you decompose your Hilbert space influence the algebras. Just like Kunz's theorem with two subspaces.
The first relation should be PHJ, right?
Yes, thank you. That's the source. Exactly right. And then here's where we get the I corresponding to the range.
Thank you. Because you use the Australian convention.
That's right, because I accidentally wrote the Northern Convention. That's right. So I was at a conference in Scotland last week. There are a lot of Australians, New Zealand, South Americans, and there are a lot of talks about this stuff, and people talk about the Southern Convention versus the Northern Convention. Whereas I always thought of it as the Australian Convention, so I think that's where it was. That's the origin that you bring at this point.
Yeah, but it's hard to judge because it was Ian Rayburn who introduced the new convention, and he was in Australia, but he's Scottish, so
that's right. But really, he did it because his students. Well, I think there's a lot of people. Just students. He claims his students forced him to do it, and I think it was because Alec Kumjian, who's an honorary Australian, came up with it. But it was sort of these ideas coming from the higher rate graph.
exactly. Kumjian pass algebra. Yeah.
The hypothesis for this theorem is the corresponding matrix A is irreducible, right?
Yeah.
That's the only assumption. Great.
And that's really where the simplicity comes from.
Can I ask some basic question again about the left side? And I'm sorry if I missed it. So tau is a functor or what?
No, so the tau sub ij is a certain function. Is that what you said?
It's a map.
I asked about what it's functor because you talked about morphisms, but you're not taking into account.
No, this is at this point, this is just sort of a intuition in the back of our heads.
So it's a function.
Yeah.
Because
The morphism idea is that that explains the Australian convention.
Exactly. Yes.
So within the set of finite paths, is really a category. And if you think of them as morphisms, then it explains why the combination.
It's a bijective map defined on a subset.
But yeah, no,
of
but
another subset.
the tau ij's are really
Yeah.
functions on subsets of this complex.
Now, the very bottom line, you know, it's a little bit unusual to see a function identity being union of functions.
Yes, that's right. So implicitly, I would mean that the functions are coherent. So that,
Or you,
in this case, they're actually disjoint. So I could write a disjoint linear twice.
you
They all-
identify your map with the graph of the map, then it's exactly a set theoretic identity.
This of course is really the identity map on the set of all things that begin with ij.
So now it's quite tautological.
Yeah, no, it is. There's nothing deep. I just wrote it in a confusing way.
No, no, that's
Let's see. Okay, so
You're right, this is sloppy, yes, you're right.
not thinking of the function as a graph makes sense, yes.
But let me get back, because I think it's very important to what Jack was saying about this interpretation. Yes, it's very convenient when you write some properties to think about the directed graph as a small category. And then finite paths are morphisms, and vertices are objects. And then many things become simpler because they say, oh, it's just fine. But it's not essential. We're not doing category theory here.
but
And then
the generalizations of this really are better understood as all categories.
Exactly.
And
Yes,
that-
higher rank graphs. Yes, yes,
and these are the graph algebras we can see, yes, on the
yes. Well, actually, these are operator algebras, which we can see once we see them as algebras of graphs.
Well, the idea is that the graph is something you can see. The graph properties of the graph determine the properties of the Caesar algebra.
Exactly.
So that you can see those properties in the context of the graph. Now, I would go further and say that there are many generalizations of the idea of directed graph that you can also see,
Yes.
and it enlarges the kind of Caesar algebras you can see.
And this is important because as much as we love Sister algebras, this is a very narrow class of Sister algebra. Okay, so they are cool, but it's really like one-dimensional subset.
So I think I said this to Soren Eiler and said, oh, well, some of us think graph algebras are actually still quite a very big class.
Yeah, because he classifies it.
Yeah.
I'm sorry to classify.
No, lots and lots to know about, just about graph algebra. Oh, lots of it.
Yes.
Okay, now, let me just say for now that the proof of Kuhn-Krieger theorem is essentially the same as the proof of Kuhn. Right, a bit more complicated, but it's the exact same idea. I won't say anything more now about that. So I'd like to say more about that in another context later on.
I have another question. If we allow A to be an infinite by infinite matrix, that is, say, row finite, does this, and assuming
Okay, so
corresponding.
I'm going to say something about this now.
Okay, great.
Just a little bit, and we'll get back to more things like that later. So, and I think this is sort of a curious part of the history. So, Kuntz and Krieger gave what I would call hints for, let's see, also maybe a matrix over the natural numbers. So I'm still not writing big enough, I guess.
Yes. Now, the moment you go below the Planck's constant, it's the trouble.
That's right. Yeah, Planck's constant happens to be very large in this quantum, which is suitable since George Gamow's pictures on the wall. Let's see. So this corresponds to multiple edges in our graph. And as you were mentioning, the other case was when the matrix is indexed by the natural numbers. So these are the infinitely many vertices. Oh, well, I guess, sorry, that's the wrong way to put it. Really infinite matrices, which is the same thing, but. So hints, I remember spending a long time trying to turn their hints into precise statements. And I had conversations with other people who also found it difficult. And watching the evolution of the definition of graph algebras towards these more general situations took many steps and was not at all obvious to lots of people, even if it was obvious to.
Recently, Joachim Kunz gave a talk in St. Louis, and it was a 1-hour talk. And he had one piece of paper which was that size, like 1/4 of A4. And he said, these are my notes for a talk. It was a 1-hour talk. So that shows you how little he needs to do something.
Good to know that there are people like this.
Yes.
So, so again, it took a long process to turn these into careful definitions and theorems. And there's two more difficulties. So there's the problem of having infinitely many edges between the same pair of vertices.
By the way, let me make this remark to the audience on Zoom. I mean, this is not a seminar talk. You're supposed to ask questions during the lecture because after 2 hours we stop. There is no session of questions, okay?
I might say that the people here are doing all the heavy lifting. Help them out by asking questions.
So please, if you have any question whatsoever, interrupt anytime you feel like it, okay? Because there is no question session. I mean, we just stop after 2 hours.
And the sound system is quite good, so we'll hear you. If
Yes, yeah.
Okay,
So
you
I have a
Go ahead,
question, Ludwig Dabrowski. So why finite matrices with elements which are natural numbers correspond to multiple edges?
I'm sorry, I couldn't.
Say it again.
Why finite rank matrices, so finite dimension matrices with natural numbers entries correspond to multiple edges? Why they do correspond to multiple edges? And
So the
only there,
the
then you
numbers
can have
from 1 up
multiple.
to n are the vertices of the graph. And the entries in the matrix really tell you how many edges to put between a pair of vertices.
Yeah.
So when there's a 1 there, we have 1 edge. And that was the case for the.
Okay, so before this was only 0 and 1, okay.
Yes,
Of course, the 0 1 matrix. And then they say,
Okay,
well, you can
okay.
easily use positive integers. And the
Okay,
same.
thanks.
Although
Thanks.
I understand that your n includes 0.
Mine does, yes.
good, which is very European.
This is again, just like
Convention.
the Northern Convention, it's just a convention.
Uh,
But it's true, one should say what one's convention is.
That's true, yes. But Ludwig, by the way, if you remember my talk in Trieste about labeled graphs, I mean, you can
Okay.
go beyond the monoid or semi-ring, actually, you need a semi-ring of natural numbers. And you can have anything to label the edges, and then instead of, we can say that you have square root of pi of edges between two vertices, and it still makes perfect sense. Okay.
Okay, thanks. But you can see this, I think. You can see this.
So in fact, I won't say anything about that particular kind of generalization.
But it's from this point of view, what you are telling is perfectly natural. Just give a label. You choose natural numbers,
Okay.
you will choose something else.
Okay, thanks.
Okay, so the second problem is, so here you might say there are too many edges between two vertices. Sometimes there aren't enough in the sense that vertex V, I'm just going to write this in symbols now, such that the set of edges whose range is V might be the empty set. Right, so these are called sources. And again, the Kunz-Krieger relations don't make sense here. So the last the Kunz-Krieger relation, the second one I wrote, in this case, we would have an infinite sum, which doesn't make sense. In this case, we'd have an empty sum, which makes sense, but isn't what we want. So these have to be handled differently, and it wasn't clear what to do. But this perspective I'm trying to provide of using this sort of, well, a kind of category model with paths and morphisms gives us a way of making sense of this. How much of this do I want to do? Sorry. So I was hoping to do the second kind of general.
Can this be extended to some sort of uncountably many vertices of some sort?
Yeah, so uncountable graphs, sure. And it's not clear exactly where you get problems and where you don't.
Yeah, well put, yes.
There's some, well, I think in combinatorial group theory, there are examples where this kind of question comes up. I don't really know anything about them, but it does seem to be something that could be of interest. So,
I don't know. It makes sense that instead of taking the matrix A in Mn of 0,1, we could take some sort of compact operator and then try to do something with it.
I don't really have anything intelligent to say about that. I don't know.
But we're talking about graphs here, but actually the theorem, the CK theorem from the previous page, it didn't have anything about A and didn't have anything about the graphs.
Oh, the A was this irreducible 0-1 matrix.
But I didn't see that at all. Right? But you talk about splitting of H into direct summons.
But the matrix A told us how those partial isometries are supposed to behave.
So they were not arbitrary partial isometries. So S's were not arbitrary partial isometries.
So I didn't write A anywhere, but I'm using these pairs I, J, and that was supposed to recall. You're supposed to remember that there's, oh, here's the matrix A, right? So the IJs are only those that are allowable according to the matrix A. So the matrix A is always in the picture in this theorem. Okay.
Maybe we choose partial isometries given by A.
Well, I would write so where that's that A of I J equals 1.
Yes.
Oh, I see.
Yes. Yeah, but it's important, you're right.
Frankly, this statement which you wrote makes mathematical sense without reference to A.
What are the
Because it's a
other
choice.
IJs in that case? Yeah.
Well, you say choose, so it might sound.
The ones which satisfy those conditions.
Syntactically,
Yes, exactly.
intelligible sentence that meant nothing within the context of the talk.
Yes,
That's right.
Yes,
exactly.
That's precisely why I asked the hypothesis of the theorem.
Yes,
A is irreducible.
Yes, he did.
so here I assume that redundancy of language is very important, but also lack of information is important where you gather things by context. But that's very dangerous in mathematics, I realize.
But for the second difficulty, if we assume A is irreducible, that should not arise, right? Because that corresponds to the corresponding row of that matrix.
Right, but I'm already here. Yeah, you're right. I've always been talking about a matrix A, but here we're generalizing the kind of matrix we talk about.
Yes.
So
No longer assume you reduce.
and in fact, I guess we might, in fact, Kunz continued the Kunz-Krieger construction with reducible matrices Sure. Again, with some hypothesis to get something reasonable, but as you consider more general situations, you're losing some of those hypotheses. So here we might think of arbitrary matrices, in some sense. Really arbitrary directed graphs. That was the idea that people wanted. What's the C-star algebra of an arbitrary directed graph? These are two new things that you have to sort out how to deal with. Okay, so what was I going to say about this? Maybe I'll omit that part. Okay, so let's now let's let E be an arbitrary directed graph. That means that, so it's no longer, we're not thinking about the matrix, just the graph. There might be multiple edges between vertices. There might be sources. There might be some pair of vertices with infinitely many edges going through them. Anything, any countable directed graph. Okay, great. So again, it's not clear what goes wrong with any of this. It's an uncountable thing, but I think the usual strategy is to say countable just so you don't run into trouble with something you've never thought about. But it's not good. Okay, so I guess for the sake of the continuity, I did need to say something else. So let me now, it doesn't let me do anything with this, does it?
I think you can move it now, perhaps. No?
Yeah, but I want to cut it but save it.
Yeah, sorry, I don't know how to do it. No, let's save everything, no.
Okay, so forget it. Let's just do
But move it on the bottom of the page.
yeah, maybe I can save it that way. That's a good idea. I just don't like his pixelization, but we'll see it. We'll save it.
But now undo pixelization, yes.
Sorry, what?
Maybe, oh, you see, there's no pixelization now.
Oh, yeah, no, it's just.
Yeah.
Yeah, no, hopefully, well, maybe I lost some of it. We'll see.
It's okay.
Close about it. I can rewrite it. Yes, there's one more variation I wanted to mention.
Can I just think of an arbitrary directed graph as the subset of the morphism set of a countable category?
I suppose. It's got some properties that not every such thing would have, right? So it's special.
It seems that
Well, but I think your question will be answered as we move on to more other general. Sure. Maybe not today, then soon. Hopefully today. So one more variation, which is actually sort of important for understanding things. So we can replace. So I didn't write this down, but I'll write it now. The second Kunz-Krieger relation, one that says the space I infinity is the union over all J of the ranges of the tau ij's. So we could replace that. So SK2, CK2, what was that? That was SI star SI is the sum over J such that A of I, so allowable edges. Again, so it's wrong. So I think I wrote it. I hope I wrote it this way. So PI was the sum over J or AIJ 1 S. J, S, J, star. So that was the second Kunz-Krieger relation. Right. So we replace this with we'll call it TCK2, which is, why does it do this? I greater than or equal to the same sum. So J such that A of I J. So the this defines a Topological version of the Kunz-Krieger algebra OA. Topological graph algebra. So, we have an exact sequence. So now we. I know why this doesn't look right to me. Is in my notes, I was doing it for the Kunz algebra, not for the Kunz-Krieger algebra. Yeah, I really have. Okay, so. Sorry, I'm just gonna. If I start to ad lib and then I don't say what I want to say. So this is now a variation, say, with Kunz algebra. So let's replace this sum from 1 to n SI star equals 1 by the less than or equal to version, inequality. And this is maybe the second Kunz relation. This we might call it the Topological version of that. This says that the ranges of the isometry, they still are pairwise orthogonal, but their span is not the whole of the state. And then we have an exact sequence. The compact operator is an ideal, and then we have the C-star algebra TON, and then ON is the quotient. So Kunz studied this also in his original paper. And similarly, the Kunz-Krieger algebra.
So the underlying graph for ON should like a star with each arrow point into the center.
So the underlying graph for ON is one vertex and arrows.
Hawaiian hearing. It does look like a star with each arrow pointing to the center. Oh, it's not. I see. One vertex. No? Okay, I see.
And the thing I wrote before. Okay, so let's talk for a little bit about general directed graphs. So I'm going to define a space X that I call, well, that is equal to all the infinite directed paths in E together with all of the finite directed paths. So E infinity union E star. And for any finite directed path alpha, we define the cylinder set Z of alpha. That's the set of all alpha X in X, well, alpha X. And of course, the source of alpha should be the range of X. Right, so infinite paths have a range, just not a source. Whereas the finite paths have both a range and a source. So all we have to make sure is that the range of our element of X matches the source of alpha, so this concatenation is defined. So it's certain subsets of this space X. And then it's not hard to check, I'll just call this fact, that if we look at the set of all, collection of all sets of differences of cylinder sets, so Z of alpha minus a union I equals 1 to n, Z of beta I, where the alpha and the beta i's belong to E star. So this is a base of compact open sets for, not in. Totally disconnected compact, or locally compact in general. Outsourcing. Topology. So here, I may be able to point out that local, it's not compact if and only if there are infinitely many vertices. Because if you have finitely many vertices, then those somehow tell you where your paths can end. It's only when there's an infinite number of choices for the final range that you get locally compact. So it's not such a deep distinction, but it is.
You can also put it in another way when you take the graph algebra of this, the identity of the unit of your algebra is just the sum of projections related to vertices.
Yeah.
The sum must be finite. And so unitality and compactness, it's the same thing for the classical situation. I'm just waiting.
So now, of course, you can always assume that the beta i's are extensions of the path alpha. Otherwise, it wouldn't affect this thing. It's not important. So alpha in E star defines a partial homeomorphism. In the sense that it's a homeomorphism between actually compact open subsets of X. Right, so alpha takes all things in X whose range is the source of alpha and sends it to all things that begin with alpha. maybe this is, like they call this tau alpha, an analogy with what we talked about before. So but again, we have, from the graph, we built this locally compact Hausdorff space with partially defined dynamics. Now, there's an important point. Okay, so in the last slide, I mentioned the Toeplitz version of ON, which you can imitate for Kunz-Krieger. And I should, so you were just out of the room. Let me just go back for a moment.
So S alpha is the source of alpha, right?
Yes. So in the Kunz algebra, if we replace the key identity by an inequality, then the algebra generated by the universal algebra by such operators now has an ideal looking like the compact operators, and the quotient is the original ON. So we call this Toeplitz ON. This was actually considered by Kunz in this paper. And there's a version of this in general for graph algebras, and that's what we're going to get out of this. Let me show you sort of where the actual analog of Kunz-Krieger algebra or Kunz algebra comes from. So the point is, I can pixelate this thing without even using it. So suppose we have a vertex with infinitely many edges having that vertex as range. So we could draw this by, so here's our vertex. We have edge E1, E2, a whole infinite sequence of edges like this. Now imagine extending each of those edges into an infinite path. Okay, we have X1, X2, and so on. So let's let Xn belong to En. I'll write it this way. So an infinite path whose first edge is the edge E sub n. So the sequence Xn in X has no accumulation point in E infinity.
But according to this topology, right?
Yeah, well, whatever topology. So if you look at just infinite paths, we think of it having the cylinder set topology like the usual Cantor set. And the point is, when you have this infinitely many edges coming in somewhere, that topology is no longer locally compact. Because here's a sequence local that has no convergent subsequence. It's very much divergent. And of course, this sequence of infinite paths converges just to this vertex D itself. So in fact, in this topology, the sequence converges to the vertex D. So it's incorrect to use the infinite path space E infinity to obtain a space for your dynamics. Remember, the key idea is from the directed graph, we should extract the locally compact Hausdorff space with some dynamics on it that we can use to define the C-star algebra. So in order to define the analog of the Kunz-Krieger algebra, we can't just use E infinity. So we define what's called the boundary of E. Is really the closure of, well, I have to be a little careful, so it's not the just most obvious thing you might say. This should be the closure, whoops. Of the maximal element. So what's a maximal path? either finite or infinite. Of course, a maximal means it can't be extended by another path. Of course, infinite paths are maximal. But a finite path, whose source is actually a source in the graph, cannot be extended because there's no edge you can put at the end of it, since no edges lead into that source of that path. So you have to use such finite paths as well in order to define the boundary. And taking the closure is what lets you get in these vertices where infinitely many edges. So let me so we give these definitions. So V is, and I'll just say infinite receiver if VE1 is infinite. V is a source if VE1 is empty. And then E infinity union, I'll write this way, E star times source of E. So this is supposed to be the set of all vertices that are sources. This is all the finite paths whose source is in the set sources. So these are exactly the maximal paths. Or the elements of E infinity union E star. So the boundary of E we define to be the closure of this set. So E infinity and E star times source E closure. And in fact, so this is an elementary fact that boundary E equals E infinity union let's see, so right, so I'll write E star times sing of E, where what I'm calling sing of E is set of V such that VE1 is infinite or empty. So the infinite receivers or the sources. And this singular stands for singular vertices.
I'm sorry, but probably due to this Australian convention, which is opposite to what I'm used to, I'm having problems understanding your convention. So when you write VE1, can you draw me a picture? How you imagine your arrows? It's
right. So here's V.
Yeah.
So this is, if you write two paths next to each other, the assumption is that the source and range match up, right? So the we have a composition. Right, so this is a composition, so the composition we write EF. Because think of them as functions. E composed with F is really F followed by E. Right, so the function F has to be done first before.
Okay. Yeah. Okay, thanks. Yes. Okay.
So this would say that
I'm
the
good.
range of F has to be the source of E.
So source is really in the middle because nothing comes to it. So the only thing that comes to the source is sort of But wait a second.
So the only thing that comes to V is V itself, the zero length.
Now I'm confused. So if source is something which does not emit
Okay.
an edge.
Now this is the curse of the English language where the word source is a noun meaning several different things. So the source of an edge is the vertex where it begins.
Yes,
But a source in the graph is a vertex with the property that there are no such edges going.
so you have the source if nothing ends in this.
Right, so there's no edge whose range is V.
Okay.
So this V is not a source, right, because there's
Yeah.
an edge going through. And the point is that if you have a finite path whose source is a source, then it can't be extended, because there's no edge whose range is that source that you can tack on to make it longer. Because
A source in a graph really means non-receiver.
yeah,
Yeah, okay.
non-receiver, sources and non-receiver. We have non-receivers and infinite receivers.
Awkward.
Or the singular vertices. All of the vertices are sometimes called regular vertices.
Singular vertices are either infinite receiver or non-receiver.
Yes, exactly. Anyway, I think this is something that sometimes people seem to miss, that the infinite paths are not locally compact if they're infinite receivers. And if there are sources, then you're missing some of the maximal elements if you don't include those as well. So the correct boundary is this way. And now let me just say that in analogy with the Kunz-Krieger case, so the theorem, we're now in quotations. That, the space X, which is I have it on the board still. It's just E infinity union E star, everything, all infinite finite paths. So X, let's just recall that E infinity union E star defines the Topological graph algebra. And the boundary of the, which is what we are looking at here, that defines. Now there, I think this usual notation is just C star of the. This is the Kunz-Krieger algebra. So to speak. So in the same way that for ON we have the Kunz algebra and the Topological algebra, one where you restrict to the boundary of just infinite paths, and one where you use really finite paths as well. So that's the same thing going on here. And now I guess maybe the final takeaway from this discussion about graph algebras is maybe what I think is the key idea. So these C-star algebras now are defined in terms of the graph, spaces attached to the graph, and the partial homeomorphisms coming from concatenation with elements. There's no reference. Generators in the
Excuse me, I have a question.
Go ahead.
What do you mean by these spaces define these sister algebras? Because if I look at it from the point of view of groupoids, these spaces generate the unit space of the groupoid. So
Yes.
it would be inside the sister algebra, the Topological
Yes.
sister algebra and the Kunz-Krieger sister algebra, right?
Right. Yes, so the first thing is to define this space. And then now I haven't continued writing it, but we still have the partial dynamics coming from concatenation. So each finite path defines a partial homeomorphism of these spaces.
Okay,
And so that's where we get some partially defined dynamics on this space. And together with those, we build a C-star algebra. And like you, I would use these to construct the groupoid and from that to construct the C-star algebra. But
okay,
that's the idea is starting with the graph, we can just define our locally compact Hausdorff space this way. We have our partially defined dynamics. We use sort of standard tools to build a C-star algebra from such information. And my key point is this one. Originally, all the graph algebra thing was, well, okay, originally it was done with the groupoid, but then it was taken over by people who wanted to use generators and relations to define the algebra, which can be done, but the evolution of the theory showed how difficult that was to guess the right relations on what might be the right generators. And this is a kind of intrinsic recipe that tells you how to build a C-star algebra without having to guess what the generators and relations might be. And that's very important when you go to more general situations where it's even harder to guess what might be the right sort of presentation, even though it's very useful to have that presentation.
So in order to obtain such algebras, what we actually do is to define a topology and using these partially defined homeomorphisms to get a dynamical system and form a sort of cross product.
Yes.
Okay.
Yes. That's exactly the whole process. So I've tried to show how it comes about in the context of graph algebras and how it sort of evolved out of the origins. What was there more comments?
I don't know.
So, well, I can ask you a question, philosophical question. So I guess a crucial point here though is that those algebras are simple, yes?
Oh, no, well, the original theory was for simple ones.
And these are not simple?
Well, in general, now we haven't, so you might say it's like taking an arbitrary 0-1 matrix that maybe isn't irreducible, or a primitive or something like that. And so you might get a non-simple C-star algebra. So yeah, so when you go to general graphs, then the question becomes, what kind of C-star algebras can we build from this? I see. And then
yeah, so thinking of that, so you guys basically declare that this is a very special type of C-star algebra. But actually, why? How do we know that there is a sea of other C-star algebras which are not of?
Oh, okay, yeah, it's a really good question. So this easiest answer to give, maybe not the most intelligible answer, is that there are these topological invariants of C-star algebras given by K-theory. And a graph algebra, so there's a K0 group and a K1 group. K1 is always free abelian for a graph algebra. And there are many C-star algebras that have non. In fact, many algebras that look like they might have been graph algebras, but you can tell them apart by using this comparison. So yeah, so that's one reason why we say it's a limited class, because the restriction on K1 is so severe.
All figure algebras are nuclear, right?
Yes, all graph algebras are nuclear.
So let me throw in 2 comments, if I may. So one is there is another way to recognize non-graph C-star algebras. If you look at the space of characters, it cannot be bigger than a circle. So you have like a classical torus of characters. It cannot be C-star algebra.
Graph C-star algebra actually complex homomorphisms on your C-star algebra.
Yeah.
Yeah.
And graph C-star algebras are notorious for not being closed on the tensor product. So take any graph C-star algebra, take its tensor square, it's not a graph. Almost. I mean, you have O2 as a counter example.
Oh, they're special cases.
That's some special cases. Okay. What else? And now you raise this point of simplicity. I really cannot resist telling you this, because precisely one of the reasons why Soren Elias is classifying some special kinds of graph C-star algebras is because the celebrated classification theorem for C-star algebras due to Elliott and collaborators, the whole program, the spectacular success. It's been a program that was completed after several decades, and under blah 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 some assumptions. We really have classifications of simple C-star algebras, I mean, nuclear unit or whatever, etc. But basically, there is a classification. So if you want to make the first move to go beyond simple sister algebras, that's exactly where you go. Graph sister algebras.
Yeah, because you can somehow look at them.
Yeah. It's the next natural step, you know.
That's natural step in intuitively or in any.
No, I guess I would say that it's a particular natural first step.
Yes.
Because it's a class that we can.
It's a natural step.
But there are, you know, you could look at like say, discrete groups acting on compact Hausdorff spaces and try to understand it in that context too.
Yes.
There are other places where you have nice situations where you can try to understand.
My point is part of the beauty and charm of graph sister algebras that they need not be simple.
Yeah, I see.
Yeah.
If I pick the disjoint union of two graphs on the algebraic level, what does it correspond to?
Direct sum.
Direct sum, okay.
Yeah, because it's,
But then if I take the characters, I could get higher dimensional torus.
When you take the Cartesian product, you get higher on graphs.
Ah, okay.
That's exactly what it is.
so that's one of the features of higher rank graphs, lets you solve this tensor product problem.
Yeah, you can define Cartesian product of graphs, but then a Cartesian product of a k-colored graph times L-colored graph is a k plus L-colored.
So the disjoint union of graphs corresponds on an algebraic level corresponds to tensor product.
No, direct
Sum.
Direct sum.
like the spaces, like disjoint union of spaces, like the sense.
We might say just, yeah, so you have, all of a sudden you have all these paths over here and all these paths over here. So
Exactly.
you just have.
We don't.
They also work for the disjoint union of countably infinite.
Yeah.
It's a C0 direct sum.
Yeah. Exactly. Yes.
Yeah, no, exactly.
Yeah. Okay.
You might say you're just adding lots more vertices and you happen to not have edges between this set of vertices. So just a big graph.
There's another very curious question which is motivated by this classification program. There is a technical condition called the UCT.
Yes.
That's such graph system algebras
Algebras always satisfy UCT.
are great.
Yeah.
Very interesting. Yeah.
Yeah.
Really nice.
For simplicity of graph sister algebras, they can be directly interpreted from the structure of the graph itself as well.
Many things can.
Yes. No, simplicity is completely characterized by certain properties of the graph. What's cofinality, which is really a way of phrasing minimality. And there's some condition on having loops having entrances.
Exit entrance, yes.
Or whatever it is.
Yeah.
Yeah, so and these are, there are conditions equivalent to simplicity that are easily checked in a graph. So that's one of the wonderful things about this class is that you can definitively check properties like simplicity, which are important.
But for me personally, this is how I fell in love with graph sister algebras as K theory. Because this graph gives you K theory on the plate. So the way
The theory of a graph system algebra can also be read off directly from the graphs.
But it's an understatement. It's just almost directly visible. For instance, any element of a case or a group of a graph sister algebra is just generated by these projections given by vertices.
Oh,
That's just amazing. I'm not saying it's a free group of vertices, of course, no.
No, but
It's generated.
and the edges tell you the relation, so you can actually go figure it out without any trouble.
you read off the whole Iliad's invariant directly from the graphs. The trig pairing.
The trace state, I'm a little less sure about.
It's non-trivial to identify the tracial state.
I think it must be possible, but I don't actually know
Okay.
how to do that. I bet it's written down somewhere, but I don't understand.
I think this is
Just don't know.
a good time since we have no seconds left. Are there any questions from Zoom? As we are closing. Now, you guys are happy? Okay. So we continue on Wednesday
At 4 o'clock.
at 4 o'clock, 4 p.m. Warsaw time. And I hope to see you there. For the time being, we adjourn. Thank you for a very nice talk. Okay. Okay, I stop recording.